Hello everyone. In this video we are going to consider the other two canonical forms for representing the systems in the state space domain. They are the observable canonical form and the Jordan canonical form. So first we start with the observable canonical form. In this form, the coefficients of the denominator of the transfer function will appear in one column of the A matrix. If you remember, in the controllable canonical form, the coefficients of the denominator of the transfer function were appearing at the last row of the A matrix. For example, here we have one, yeah? So these minus 24, minus 26, and minus 9, they were being obtained from the coefficients of the denominator of the transfer function. And for the rest of the matrix, for the rest of the A matrix here, we had zeros for the first column and a diagonal submatrix with ones at the diagonal for the diagonal elements. And we also had the values obtained for B and C vectors. Here, in the case of observable canonical form, we will have one column of the A matrix, so a single column, will receive values directly from the coefficients of the denominator of the transfer function. This form can be obtained following the steps that I'm going to show you. So if we assume that the transfer function of the system is given in this form, y over u is equal to b0 s to the power of n plus b1 s to the power of n minus 1 plus bn over s to the power of n plus a1 s to the power of n minus 1 and so on and so forth up to an. So please pay attention that here the coefficients for s to the power of n at the denominator is equal to 1, and in case the polynomial in the numerator has a smaller degree, then we might have b0 equal to 0 or b1 equal to 0 and so on and so forth. Now, we can rewrite this transfer function in this form. The denominator multiplied by y of s will be equal to numerator multiplied by u of s. And then we can factorize the expression. We take everything to the left side and factorize it based on the powers of s. So we'll have s to the power of n times y from here and b0u from the other side. So y minus b0u plus s to the power of n minus 1 times a1y minus b1u, and then we will have a-n-y minus b-n-u equal to 0. Now we can divide everything by s to the power of n, both sides. So for the first term, s to the power of n will be cancelled with the s to the power of n at the denominator, and then we take everything to the right side except y, and we will have y equal to b0u plus s to the power of n minus 1 over s to the power of n will give us 1 over s plus 1 over s times b1u minus a1y, and the last term will be 1 over s to the power of n bnu minus any. So it comes from this term. Now we can construct a block diagram for this system. Here, as the main output, we have the y signal. Y is equal to b0u. So u is the input to the system. Y is equal to b0 times u plus 1 over s times a set of a sum of some other terms. Okay, so for this, for 1 over s, we will have the integrator here, And then the input to the integrator will come from this summation term. So these will come from here. And then we can move backwards until we reach the last term. The output of each integrator here will give us one state. So here we call this indeed as xn, the output of the last integrator, the rightmost integrator. Then the previous one will be called as xn minus 1. And the first one that we have here, the output of the first integrator will be called as x1. So you can see the block diagram over there. Over here we can indeed check it again. So xn will be this expression here, xn here. So we have xn equal to the expression that we have here, 1 over s times b1u minus a1y plus 1 over s squared times b2u minus a2y up to 1 over s to the power of n bnu minus any. If I want to construct xn dot, which is the signal that we receive here at the input side of the integrator, so xn dot is here, we need to multiply everything by s. So xn dot will be equal to will be equivalent, yeah, let's say, because xn dot in the time domain is equivalent to s times xns, and this will give us b1u minus a1y plus 1 over s times b2u minus a2y plus 1 over s to the power of n minus 1 bnu minus any. So b1u minus a1y, these two terms, you can already see them here. So b1 times u minus a1 times y, you can see both of them there, then plus some terms. And this term will be considered as xn minus 1. Now that we have the expression for xn minus 1, xn minus 1 is equal to 1 over s times b2u minus a2y plus 1 over s to the power of n minus 1 times bnu minus any, we can find the expression for s times xn minus 1, which is equivalent for xn minus 1 dot. And indeed that will be the input to the next integrator. So here we have xn minus 1, therefore this will be xn minus 1 dot in the time domain. And obviously we will multiply everything here by s. So we will get b2u minus a2y plus 1 over s times b3u minus a3y plus 1 over s to the power of n minus 2 bnu minus any. And again, this b2u minus a2y, you can see them here. these are the indices are different, but you can see the relation. And then the rest are indeed this state again. And we just need to take this approach until we arrive at the last state, which is x1, and then here we will have the x1 dot. Therefore, in terms of the expression for xn dot, we have the expression in this form: xn dot is equal to xn minus 1 minus a1 times xn plus b0u plus b1u, and at the end we will have the x1 dot, which is in this form, minus an times xn plus b0u plus bnu, and then for the output we'll have it as y equal to xn plus b0u, as we have here. Yeah. Now we can put everything in the form of a matrix. We have x dot equal to ax plus bu, y is equal to cx plus du, and therefore we have A as this matrix. So we will have the coefficients which we had at the denominator as the last column. They will form the last column, minus an minus minus 1 till minus a1. The first row will be 0 apart from the last element, and the rest of the matrix will be in the form of a diagonal submatrix with 1s at the diagonal elements. For B, we will have it in the form of a vector. In this case, since we have a single input, B will be equal to bn minus an b0, bn minus 1 minus am minus 1 b0 till b1 minus a1 b0. And then for the C vector, it will be in the form of a row vector with zeros everywhere except the last element, which will be equal to 1. And D will be equal to b0. And obviously, if the order of the numerator and the denominator are not the same, then b0 will be equal to 0, and we will not have the feed-forward pass indeed. So that's what we have for the controllable canonical form. Please keep in mind that in this case, for the observable canonical form, that in this case, only the last column of the A matrix will be obtained referring to the transfer function coefficients at the denominator. And for the rest of the A matrix, we'll have it in this form. For B and C, you can see how the values for the vectors are obtained. The next canonical form that we have is called the Jordan canonical form. In this form of representing the systems in the state space domain, the pose of the transfer function will form a string along the main diagonal of the matrix A. So for matrix A, all the elements will be 0 apart from the ones on the diagonal, and those diagonal elements will be indeed the pose of the transfer function. In this case, we are going to consider only when we have a distinct pose. We don't have multiple pose for the transfer function or the complex conjugate pose. So this will be the simplest case indeed, but you can also consider the more complicated cases if you wish. So in the Jordan canonical form, we will have the state space model in this form. A matrix will be all zeros apart from the diagonal elements, which will be in the form of lambda 1, lambda 2, lambda 3 till lambda n. For the B vector, we will have it in the form of R1, R2, down to Rn. We will see how to obtain them. And for C vector, C matrix, it will be full of ones. And for the D, we will have D0 if the order of the numerator and the denominator are the same. Here you can see how those values are obtained. We have the transfer function in this form: y over u is equal to d0 s to the power of n plus d1 s to n minus n up to dn, and at the denominator we have 1 times s to the power of n plus the rest of the terms. Then we can rewrite h of s in this form. It will be equal to d0 plus r1 over s minus lambda 1 plus r2 over s minus lambda 2 up to rn plus rn over s minus lambda n. In this case, all the poles that we have for our transfer function are distinct again, so this is important to keep in mind. There are no repeated poles. We call our i's r1, r2 up to rn. They are called as residues of the reduced transfer function if we subtract d0 from h of s. So y of s will be written in this form, d0 times u, so this is the feed-forward unit path, plus r1u over s minus lambda 1 plus the other terms. And then we will take each one of these terms that you see here, r1u over s minus lambda 1 will be our x1. r2u over s minus lambda 2 will be our x2. And rn times u over s minus lambda n will be our xn. And once we have them in the Laplace domain, we can find the equivalent ones in the time domain. So for the last one, for example, let's say xn is equal to, in the Laplace domain, is equal to rnu over s minus lambda n. So we will have s times xn minus lambda n times xn equal to rn times u. Then in the time domain, we will have it in this form, xn dot minus lambda n xn equal to rn u. And therefore, xn dot will be equal to lambda n xn plus rn u. And it is similar for all the other states, xn minus 1 x1 dot, they will follow the same or the similar pattern. And you can see it over here. For the output, on the other hand, we will have it simply equal to d0 times u plus x1, x2 up to xn, because we picked all those terms as the states. And now, considering all those in mind, we will have the system in this form. So x dot will be equal to a times x plus b times u, and y will be equal to c times x plus d times u. You can see how the A matrix will look like, how the B matrix will look like. It will include the residues. C will be all ones, and D will be equal to the 0. You can see over here how the block diagram system for the Jordan canonical form will look like. Y is equal to the sum of the states. So x1 comes from there, x2 comes from here, x3 comes from here, and therefore y is equal to x1 plus x2 plus x3 in this example. Indeed, we can go up to xn plus d0 times u. And then for each one of x1 dot, x2 dot, xn dot, we have it in the form of summation of r1 times u plus lambda 1 times x1, or lambda 2 times x2, or lambda n times xn. So the block diagram realization in this case is kind of straightforward. We will have the feedback loops for each state, and then for the output we will have all the states added to each other plus d0 times the input. Alright, so I think that's all for this video. I hope you have learned how the observable canonical form and Jordan canonical forms could be formed. Later we will see when these kind of state space representations could be useful compared to the controllable canonical forms. Thank you for watching, and see you in the next video later.